All right, good morning, everyone. Welcome to the third day of the ICFP program. Very happy to introduce our keynote speaker for this morning, Rizkallah. She is a senior lecturer at the University of Melbourne. PhD is from Max Planck Institute in 2015. In between, she postdoced at NICTA and UPenn and was a professor at UNSW for a few years before her current position. Her work is on formal verification and making it, practical and easier to apply in specific domains, especially through domain-specific languages. So areas like algorithms and security and social choice theory, which I have not read the paper yet to find out what that means. But today I think we'll be hearing about system software and applying tools to that. So let's welcome Christine.
Thank you, Matthew, for the introduction. So today I'll talk to you about two projects that we've had running since 2013, I think. The Cogent project and the Dargent project. But before we go there, let me make sure I'm displaying this correctly. There we go. So before we go there, what is the motivation of this work? So software verification in general, you want to verify your software to make sure it's correct, but it's not enough to verify applications like algorithmic libraries or crypto protocols and whatnot. It's also important to verify the underlying systems software, so underlying microkernel, but also things like file systems, device drivers, and network stacks. Because if you only verify your applications, you could have a bug in your file system, and an attacker could exploit this bug and then completely undo any of the guarantees that you already have. So where did verification stand a while ago? So I think there's a lot of good work in interactive theorem proving. Two projects that I want to highlight are CompCert and SEL4. So I think both these projects stand out in some way. And the reason is that, in my opinion, the reason is that they did not compromise on trustworthiness or on efficiency. So CompCert is an optimizing C compiler, generates efficient code, and it's verified in Coq. And SEL4 is a microkernel that's verified in Isabelle Home. And while both these projects did not scale down what they want to verify, they were an enormous amount of effort, and it took various PhD students to verify them. SEL4 took about 25 person-years for about 10,000 lines of C code. And if we want to scale this effort up, we need to do something a bit differently. So I think the problem is that verifying systems by just all the way starting from C by brute force is extremely costly. And so the aim of this work is to reduce the cost of verifying software and without compromising on the efficiency of the software that's being verified, and without expanding the trusted computing base that we have, so without adding more and more tools. And the idea here is to handle one area or one field at a time, not necessarily having domain-specific languages that work for a particular type of software, but just at least languages that are restricted and sufficient for verifying software within a certain domain. And in the past, we've looked at verifying file systems. Currently, we're looking at verifying device drivers, and in the future, we want to look at network protocols. And in order to reduce the effort involved in verifying software, we want to abstract. We want to automatically abstract both the code. So maybe when systems folks or algorithms folks want to implement code, they typically want to implement it in a low-level language. And it's not because they like pain and suffering. It's just because they want to have efficient code, I think. And when we want to verify code, typically you prefer to have mathematical functions because they're easy to think about, easy to prove things about. You don't have to worry about pointers and memory and guards and all of that. This is in regard to code. And then in regard to data, when you have very low-level systems, sometimes they want to have a handle on how data structures are implemented in memory. So they would deal with things like bit fields or just specify bit by bit where things are laid out so that they can operate on this data efficiently. And it's hard to get code right when you're thinking about an array of bits in memory and bit shifting and whatnot. So I think both in terms of implementation and verification, it would be preferable to think about algebraic data types if you could get away with that without compromising efficiency. So yeah, so the two projects that I'll talk about, one of them is Cogent, and it focuses on the automatic refinement of code. So basically, how do we reconcile these two views automatically? And the other project is called Dargent, and it has to do with also reconciling these two views. Okay. So here's the general approach that we've taken. In order to reduce the cost of verifying software, we've decided that we want to use functional languages because these increase productivity in terms of verification. I think also in terms of implementation, you can write less lines of code. And we also want to have type systems that can automatically enforce safety and security properties. And why type systems? Because programmers are comfortable with type systems, and if they can automatically enforce properties that we want to have and maybe even provide a proof that these property holds, then this is a very lightweight way of getting formal methods somehow. And certifying compilers are verified compilers, and the reason we also are interested in these is because they automate a large portion of our verification. So by basically abstracting like low-level code into functions, and then we can prove things about the functions manually on top of that. And yeah, so why were we interested in file systems? So this remained an open problem for a long time, and it was posed as a grand challenge back in 2008. And various groups worked on this problem. And I think the reason this problem is quite difficult is because there are many file systems. For example, Linux has about 50 of them, and each of them is about 5,000 lines of code. So I don't know, for 10,000 lines of code, it took 25 years. You do the math. And one thing about file systems is also they're very boring. So a lot of the code is extremely tedious, and boring is good. It means we can automate things. We can have a small language, and it can cover a lot of that code. And in order to verify file systems, what we decided to do, and by we, I'll tell you who we are on the next slide, we created a language called Cogent. It's a restricted language, and I'll tell you what that means. So you can't implement, it's not Turing complete, you can't implement everything in Cogent. It's functional, and it has a linear type system and the certifying compiler. And the certifying compiler generates code and proofs, and I'll show you a picture of how this looks like in a minute. But yeah, this project has been going on since 2013, and many people over the years contributed to this project. Liam heavily contributed to the language design, and Zilin as well as the implementation. Gabi contributed to starting the project. More recently, Vincent and Louis have contributed to this project, and many other people have made various contributions. Some of these people fall in the systems domain, others fall in programming languages, others fall in verification, and like we were all working together in sync, back and forth, in designing this language, and I think that was quite important to help with the design. I'll tell you what the results were, and then I'll get a bit more into the detail of how we went through it. So yeah, it's a functional language with a certifying compiler and a linear type system, and I'll tell you also what that means in a moment. But basically, we implemented 2 file systems in that language, one existing file system, and one that we designed from scratch. It's a journaling file system that's quite complicated. So Sidney Amani designed this for his PhD project. And we verified the functional correctness of 2 key Bilby file system operations. And in this verification, we heavily relied on automating large parts of this verification because we implemented them in Cogent and then used the certifying compiler to prove that it's similar to the C code, and then verified the file system operations on top of the functional semantics of the Cogent code. So yeah, so Bilby was first implemented in C and then implemented in Cogent, also so that we can compare the performance and convince ourselves that the code that we're generating from Cogent is efficient and has similar performance to the handwritten C code. So yeah, in case you want to refer to this work, we have a recent paper that subsumes other papers, and this is the language one, and then the systems work is still from 2016, the write-up. And what is a linear type system and why do we want it? So linear type system is really simple. So variables that have a linear type must be used exactly once. Okay? And why do we want that? For many reasons. So when we have a linear type system, that allows us to generate efficient imperative code because and I'll show you in a moment why, but basically the idea is because we don't need garbage collection. Although we have a functional language, if you know everything is used exactly once, you can replace it by something else and allocate a bunch of memory at the beginning, reuse it, and free it at the very end. And it helps with memory management because it gives us a functional view of the language and an imperative view of the language, a functional and an imperative semantics of the language that happen to coincide. And that means that nothing that has to do with pointers or memory can ever go wrong. So the way, if you implement code that has, and ensure that all your pointers have a linear type, you get automatically that you don't have any memory errors, okay? But most importantly for me is that it gives us a really nice higher order logic representation of the code that is easy to reason about because we don't have to think about memory at all. So you don't have like the state is threaded through in a way, so you can think of everything as a function. You have a functional semantics for the Cogent language, and on top of that, the higher order logic that you don't get monads over state, you get just really nice, simple functions. And okay, what does the Cogent language look like, more or less? I'm not going to introduce the full syntax, but it has the typical let and if and operations that you'd find in a functional language, but it also has, we also have records in Cogent, and because of the linear types, you have to kind of, if you want to use everything exactly once, you need to use every field in the record exactly once, so you kind of need to be careful in tracking what have you taken and when did you put something back so that you can take it again, so that you don't access any of the fields more than once, right? So we have these take and put operations also. Now, Cogent doesn't have recursion or iteration built in. Instead, it has a foreign function interface to template C, and we have a library of data structures that are implemented in C with iterators over these data structures that we can access back and forth. And I'll tell you how this plays into our verification story a bit later in the talk. And yeah, and then loops are implemented as iterators over ADTs, which systems folks tend to like because even if we offer them recursive types, they're not going to use it. So, okay, so here are the Cogent types that we have. So we have words of various sizes. Actually, we have like 1-bit words now as well. We have records, variants, abstract types, function types, polymorphic types, yeah. And yeah, so I'll give just a couple of examples just to show you how the linear types work. So linear types are used exactly once, X is used twice, this doesn't work. X is used 0 times, this doesn't work, okay? X is used in the then condition, but not the else condition, doesn't work. This one works. So you have this like style of threading things through. So X is equal to some data, you can update X, save it in a new variable Y, and then give Y back. So each of X and Y is used exactly once, okay? So now looking at this, you can think about the C code that's generated from that, and the C code will use the same memory location to store X and Y. If I know every pointer is used exactly once, then I could just like, whenever I have a variable, I could just replace it by its value and reuse the same memory location for the next one and the next one. And I don't need any garbage collection until the end of the entire process. So, okay. Now, linear types, it sounds a bit painful to have that. And why can we get away with all these restrictions on the types and also like with the ATTs and whatnot? So the idea of the project is we want to write as much code in Cogent as possible, and that will simplify its verification. And then we want to write a small portion of the code in C and verify that code manually, compose it with the Cogent, so the composition happens automatically using our framework, and reuse these small parts over and over, okay? So if these small parts are, for example, arrays or trees or data structures that are used across various file systems, then we could just reuse them and amortize the effort of verifying them over all these various systems. Okay, so here's a picture of how this looks like. You have a Cogent program, so let's say it's an entire file system. You pass it to a certifying compiler, and a certifying compiler gives you out 3 things. So it gives you out efficient C code. It gives you a pure higher order logic functional specification of the code. This is not the specification you want at the end, right? This is mirroring the Cogent code, and you still want to maybe prove additional things on top of it manually. But it's ideal for at least reasoning about the Cogent code or about the system in general. And most importantly, we don't just get like memory safety out of our certifying compiler, we get a full refinement proof. Namely, we get a proof in a theorem prover that says anyway, the higher order logic can behave in at least as many ways as the C can behave, right? Or more or less they do the same thing, right? So, and that means that anything that we prove about higher order logic, we can compose that theorem with our compiler generated theorem and know that it also holds for the underlying C code, okay? So yeah, I think this is really the main idea, and this proof is really like actually a sequence of many, many smaller proofs with languages inside, with various embeddings of Cogent and whatnot. But yeah, this is the basic idea, okay? And we also get a proof that a program is well typed, for example, like a generated. Okay, and then it's not only that. So I said that Cogent has a foreign function interface to C. So actually, yeah, so that C code can be passed to the Cogent compiler as well. For example, let's say a C ADT or a template C ADT. And then the Cogent compiler will link the two and will give you a bunch of assumptions about the C code that you may or may not want to discharge in order to get the final theorem about the entire system. So the pure functional spec at the top is a functional specification of the Cogent along with the C. Okay, so you'll pass the C code, you'll pass a specification of the C code in higher order logic, and you'll have to do a manual proof that the C corresponds to the functional specification you provided. You also have to prove an additional theorem saying C does not mess with Cogent. so we've been like tracking memory very carefully. You can't just, the C part of the program cannot just go in and sweep things under my feet. So it has to respect the Cogent type system, and it also has to respect its functional spec. And then Cogent gives you the composed verification for the entire system for free in a way. Okay, and yeah, recently we've finally verified our array library for C, our word array library, and showed it on some example, the same one that was used for the file systems. Okay, so what are the results of this project? So we were able to implement efficient Cogent file systems. I mean, there are some narrow cases where it's less efficient than handwritten code, but overall, it performs within maybe like 10% difference to handwritten C, which is by system standards quite efficient. So we implemented 2 file systems. And in these file systems, each of them was about 4,000 lines of Cogent and an additional 2,000 lines of C code. Okay, so for the Cogent parts, Cogent dramatically reduced the cost of verification. So it was about a third, right? Like for SEL4, it took about 1.65 person-months per 100 lines of C code. And for the file systems, it took 0.38 person-months for 100 lines of Cogent code. And the Cogent and the C were about 1-to-1. So the Cogent file system along with the C and the C file system were almost 1-to-1. It's a bit surprising because you think the functional code makes things a bit less, I don't know, like smaller, but I guess we have a pretty sparse notation for Cogent at the moment, and you have all this linearity, so you have to keep passing things around. So it's about 1-to-1 to C. But that still saves us like 2/3 of the effort for about 2/3 of the file systems. And this is to be taken a bit with a grain of salt, because one of these is about verifying operating systems, and the other is about verifying file systems. And I already mentioned that file systems are kind of boring, right? So maybe they were easier, I don't know. But yeah, like 2/3 is a big deal. So even if we say it was half the effort, that's still worth investing in. Okay, I did say a small part in C, and now I'm saying a third of it is in C. So what is that about? How do we deal with that now? So the follow-up Dargent project, part of it is about reducing these 2,000 lines of C code, and the other part is about also being able to verify more code, like device drivers, which would be completely impossible without data layout representations and whatnot. So yeah, but like some of this is reusable, right? So some of it, for example, is in, yeah, like the ADT libraries. And these are fine because, yeah, we verify them once, reuse them many times, that's okay. For other parts that were the most painful, and I'll show you that in a couple of slides, but it's basically the type mismatching between the layouts that Cogent picks, because the Cogent compiler is just a compiler, right? So you give it the Cogent type, it will generate a C type in a very standard way. Record converts to struct. And the C that you get is not exactly the C that the system folks want or that surrounding systems expect. So you have the file system, it lives among other pieces of systems code, is not the layouts that they expect. So you have this layout mismatch, which means that we have to serialize and deserialize information back and forth. And that is horrible. It's error prone. It's really boring code. We don't want to verify it by hands. So yeah, so this is the type mismatch problem. And yeah, and another reason is like sometimes systems folks just want to use bit fields or want to have strange padding and alignment, and none of these can be expressed by a native Cogent type, so they'd have to implement everything that they want on these types in C. So our old solution was to define an abstract type in Cogent, a logically equivalent type, an abstract type in Cogent, and implement it in C and have these marshalling, unmarshalling operations back and forth. They're error prone, they're inefficient, you have to do copying and whatnot, and they're very hard to verify. So can we do better? Okay, still the next half of the talk, so yeah. Yeah, we can shift towards more Cogent and less C, and also we can probably improve our verification interface between Cogent and C. So, yeah, so I keep mentioning this interface between Cogent and C. So yeah, like Cogent programs are part of a larger system. For example, even if it's an entire file system, it's gonna run, be surrounded by other systems code. And they're connected to these outer systems through a foreign function interface. And yeah, and most of what's implemented in C at that point was ADTs and also this matching up of layouts. So I'll focus on the matching up of layouts. We have a few ways to get around this, or like choices there, right? We could only use Cogent types, but then we won't have any C integration, so that's not an option. We could only use abstract types in C. We're not going to have to do any conversion or anything, but then we don't benefit from Cogent at all. And we could do conversion by copy, so that would not be efficient. We'd have a lot of boilerplate to actually do the copying, but we would be able to integrate with C. Or the last option that makes verification people shiver a little is we could just do conversion by cost. Right? We could just say, take this, pretend it's something else. I'm done here. What can go wrong? Actually, cost is not bad per se. It's only bad if you don't actually know how things are laid out. Right? So imagine you had a language in which you could specify how things are laid out, and you got some form of guarantee that they're laid out as specified, then you can cost away, right? Like if you know the first bit contains something and the second, third, and fourth bit contains something else, you could view them as whatever type you want, as long as you know the type contains these things. So as long as, sure, like cost with more information. Do it properly. So that is basically what we did with the Dargent language. So Dargent, you'll see that there's some overlap in people. All of us have different affiliations. There's not a single affiliation that, oh no, that's not true. Vincent and I have the same affiliation now, but everyone else has different, I'm not on the slide, so everyone on the slide has different affiliations. Yeah. But yeah, so Zilin was the main person designing the Dargent language for his PhD. Ambroise was a very heavy contributor to the extension of the certifying compiler framework for this. Liam and Gabi helped with initial designs of the language. Craig helped with all sorts of compiler issues, and Vincent was everyone's advisor on how to do Isabelle ML. After 2 years of using Isabelle somehow. So yeah, so Dargent. What is Dargent? It's a data layout specification language with verified data refinement from algebraic types to their memory layouts. And you're allowed to pick these memory layouts down to the bit level. So basically, you as the programmer can sit down, write your algebraic types, define how they're laid out declaratively, and then have the compiler take care of generating access functions to access these data types from the memory bit array that's below, and it gives you a guarantee that it's setting and getting things to the right places. Okay, and then you can just do everything on your algebraic data types, implementation-wise, verification-wise, and not worry about these bit-level representation of your program. So how does this exactly look like? We'll see an example, but basically, you had your Cogent type before, Cogent program before, and you passed it to the compiler. You can have your Cogent program again, use the same types, pass it to the compiler, but now you're also passing this data layout specification for each type, or for each type that you want to specify the layout for. And then what you're getting out is, again, like just C code, but now lower level C code. So C code that instead of using structs and things like that, you have an array of bits in memory and you're managing it. And and then this can, I don't know, run on underlying devices that expect a specific layout, for example. More concretely, here's an example. So when we had Cogent code, say a record that has a word of size 32, you could access that field in the record in the usual way. So you write r.a or set it as r.a equals 4. The C code that we generated for that was what you'd expect. So just a struct, again, with an int, and then you would set and get this way. So get the field A and set the field A. So this is all an algebraic view of the data structure, right? With Dargent, now the C code that we're generating is lower level. So we're generating an array of bits in memory, and we're generating two functions, two functions for every field of every record, for example. So a getter and a setter, and the getter, and so you still have that algebraic view of you could just like call the function get and call the function set, and not worry about where it's getting and setting into the array. But under the hood, what these getters and setters are doing is that they're getting and setting from the right place within that huge array of bits that's created according to the specification that you're providing. And these are generated by the compiler now. So they're generated by the compiler as specified by the layout that's provided by the programmer, and they allow the programmer to code using algebraic types. Okay? Here's an example with some color in it. I don't know about the font, but at least it has some color. So you have a record, and it contains three things. It contains another record, a pointer, and the variant. And now you could write that so it has the record, pointer, and variant. And now you could define that the layout of this record is as follows. It has a record layout, a pointer layout, and a variant. And here, for each field in that record, you could give a size in bits and bytes. So capital B is bytes, small b is bits. So you could just say, for example, X takes 4 bytes, Y takes 1 bit. Okay, so booleans in C, we used to use either, I don't know, some 8 bits, I think, or a character, something like that. Now we could represent them using 1 bit. Pointer, you could, and similar for the variant, you could just say the tag of the variant takes 1 bit. The first alternative takes 2 bytes, and the second takes 1 bit. So then you could reuse the same memory for the 2 alternatives based on the value of the tag. So here, you could also define an offset. So the pointer, for example, we first put X, and then we put Y, and then we put the pointer at offset 8 bytes. So then, as defined by the user, I went to byte number 8, put the pointer there, right? And then you could define that the variant is starting at byte 5. Why 5? Why not 4? Because I defined it that way. I could have defined it however I wanted. So At by 5, I start putting the variant, I put the tag, it's 1 bit. If that bit's 0, then you lay out X here. If it's 1, then you lay out the Y there. Yeah, depending on the value of the tag, okay? There's some syntactic sugar on top of that to make it less verbose, but basically you can define everything down to the bit level if you want to. And yeah, and how does this look like in terms of the compiler certificate that we're getting? The certificate is the same. However, we're getting it for lower level C in a way. Like the C code now, instead of using structs and whatnot, we're using bits and bytes in memory. And it can operate on these getters and setters that are generated by the compiler, right? So this compiler is generating getters and setters on the C level. And yeah, and the C code uses these instead of just the struct operations that we used before. Yeah. We're also generating some additional theorems just for sanity checking. So, or also because we want them. So in addition to whenever I want to reason about my program, I'll still think about the higher order logic functions, and I don't care about where things are laid out. This doesn't come up. Actually, it's surprising how fast we could fix the compiler, update the compiler to account for Dargent, because the only phases that we had to change were the lowest phase, like going from Cogent's imperative semantics down to C, right? And also the typing proofs. So and does anyone have any questions? Yeah.
I missed how you check that the struct definition is in correspondence with the layout specification.
Yeah. So so that's the other bit that we had to change. I was waiting for that exact question. Thank you, thank you, Nick. The other bit that we had to change is the well-typedness proofs, right? Or we had to add more proofs. Namely, one thing that we want to check now when we're checking well-typedness is also checking that the layout matches the type. For example, if I say this is a word of size 32, this has to be 4 bytes. If this was 3 bytes, I need to get an error from the compiler saying there's a layout mismatch. And I do get that error from the compiler, right? And if the compiler accepts the program and the layout matches the type, then now we're also generating proofs that the type and the layout match, okay, if they're accepted by the compiler. So we've extended also the well-typedness, or I shouldn't say well-typedness because we were very careful to keep them separate. We don't want to complicate our type system any more than it needs to be. So we have the well-typedness checks, but we also have checks that the type and the layouts match, okay? And then this additional theorems that we get is just telling us that the getters and setters that we're generating are getting and setting to the right places that are defined by the programmer. So when I'm proving something about my system, like properties about my Cogent program, I will not need to talk about these layouts at all, right? I just need to talk about the higher order logic functional specifications, which look exactly the same as the ones we had before. But when I want to link this to other surrounding systems, and if I want to do my cost, right, I will need to know that where these getters and setters are getting and setting, so that when I want to cost them as something else, I want to know what corresponds to what, right? So I could use these additional theorems then. Okay. Any other questions before I keep going?
Just a small one. How do you know that the layout that you are verifying matches the layout that the C compiler is going to use in the end?
the C compiler will not use a layout because we're generating, if you mean from the surrounding systems or just this system? So here we're generating an array of bits in memory. So the C compiler will not be doing anything at all, right? Like there are no structs or unions or anything in C that the compiler will decide on. For surrounding systems, if the surrounding systems also use arrays of bits in memory, then the C compiler continues to not have to do anything. If, however, they decide to use structs or whatnot, we'll do whatever the systems programmers always do, which is they know how the compiler will lay things out because they're gurus, and I don't know how they know, but they seem to know, assume maybe. And they can decide to either assume that, axiomatize it, or just force the compiler to not do anything and specify their bit fields or arrays of bits in memory again. So so that's one thing we would do. So I would prefer if people did not rely on the compiler for anything and just had like arrays of bits. Look, they magically match. We don't have to rely on the compiler for anything, but if they want to assume how structs are laid out and use that, that's up to them, I guess. They'd have to axiomatize that. One thing I'd love to have in the future is Dargent for C. Then allowing systems programmers to write structs and have a C compiler lay them out as specified by the programmers. I think that would be also nicer. Then they can use the algebraic types in C. They don't have to assume anything. They can also specify on the C side how they should be laid out. Yeah. So but that's not something that exists at the moment.
So, Ben Gomari, well typed. One thing, especially when working with hardware and potentially in concurrent systems, where you're exchanging sort of bitwise data around, is that it's not necessarily the eventual state memory that matters, but also the order in which you perform individual, the order in which operations occur within a particular structure, right? If I have an algebraic representation of my sort of conceptual data, I will actually need to take care to mutate things in a particular order to ensure that either the hardware does what I expect it to do, or that another thread running on my machine will see things in the right order. And yet, this sort of degree of detail is definitely abstracted out in the ADT in your conceptual types, I guess. So is that something that I guess you cannot rely on Dargent and a more abstract representation for in these settings, or is that something you thought about?
I mean, what we did is we introduced the 1-bit type to Cogent. And if you really need that level of low-level details, then you will not use an algebraic type for that thing. Right. If you need it up to the bit level, you'll define that it's a bit in Cogent. And then you'll know that it's 1 bit or something like that. But yeah, you're asking, what if I want to know something about the layout at the top level? Is that your question, or?
The question really is one about ordering. So if I have, if I have a sum, for instance, maybe we can take this offline. Actually, it's probably more detailed.
Okay, but yeah, okay. I'm not sure. Yeah, let's take it offline because I'm not sure what the question is. But yeah. Yeah. Okay. So yeah, what are the results of this project in a nutshell? So we have the language, the data specification language. It also supports polymorphic layouts and endianness annotations. So Cogent has polymorphic types, so we wanted to also have polymorphic layouts. When these polymorphic types are monomorphized, you can check the typing and layout matching at that later step. And endianness annotations, which was something that systems folks asked for. The certifying compiler generates these getters and setters to lay out and access types as specified, and also they continue to produce this Isabelle Hall proof. That the C and the Cogent correspond, but also that that the C code respects the Dargent layouts. The implementation and manual verification can operate on the algebraic types, and we verified the tiny timer driver and the power control system using Dargent. We also verified an LED driver, but we haven't published that yet. Like to verify more drivers using Dargent because these were quite small. We, like the programming language and verification folks implemented these. It would be nice to have some people who are interested in systems who could help us understand more drivers. It was really easy to do the verification. I mean, these are small, but like the C code was horrible, bit shifting, stuff like this. As soon as we understood what the C code is up to and understood the spec, it was really easy to write the Cogent code. It's just a few lines of code because now we just lay it out. It's like get it, shift it, put it there, done. So a lot of these drivers is just like take this thing, take this other thing, put them together like this and put them out. So it's all getters and setters and combining, and all of the horror goes away. So the verification was also trivial. The biggest of these, which was quite small, took about a week to verify once we had the implementation and spec. So so for more information about Dargent, check out our paper from earlier this year. And what's next? Other directions we took and are taking are horizontal composition of Cogent and C. So I said that we can compose proofs of Cogent and C, but we have had the framework for a while. We haven't actually tried it out. So now we tried it out. We've verified the C array implementation and verified the combined system through the Cogent FFI, and it works. The person who did it likes it. I don't like it. So I think one thing about the C code is you provide the C, you provide the specification, and you kind of have to prove that it's in sync at every level of Cogent. I said there are many levels of proofs, and you kind of have to mirror these on the C side manually. The person who did it primarily did this like Lewis, because he said it guided his thinking. One level was getting rid of like memory, like abstracting away memory. One level was abstracting away, going from memory free to blah. So it kind of made the proofs easier, but I think there's a lot of repetition, a lot of room for automation there, automating parts of these. Or even better, what we're looking at next is how to allow people to prove stuff about the C code, say using separation logic and composing these proofs with Cogent proofs, like the notions of separation from linear types and from separation logic should coincide. Don't look quite visually the same for us. We have a property-based testing framework for Cogent. And that's because we want to keep updating the language. Verification will not always keep up with language development. So we want to do some testing before we start verifying additional features. And also because we want to verify like above the the automatic verification is up to the higher order logic level, and we want to go. We can go some steps higher if we do testing, right? You could just test high-level properties on top of that, or test the C code, the combined system, without verifying the C bits manually, before verifying the C bits manually and whatnot. Professor Tege in Germany developed a tool called Gencot. It automatically converts C to Cogent. It's under development. It confers a fair amount of C, and the idea was they'll automatically convert C to Cogent, and then convert Cogent back to C, and now get the higher order logic specification about the C that's generated and proof stuff on top of that. They're using it for verifying what was it? I forgot. Some code, I don't know, something to do with keyboards. Maybe it was the driver as well. It's quite exciting that other people are actually developing stuff and using this. One thing that we're doing is adding primitive recursion to Cogent and Dargent. Although it's not the top priority for systems programmers, I don't think it's that difficult, and it's kind of a functional language. I think it should have primitive recursion. What is a little bit more difficult, or not difficult, but just something we had to do, was to implement a termination checker to ensure totality, because we want to make sure the higher order functions that we're getting are still nice to reason about in a theorem prover like Isabelle. And so Cogent functions should terminate. And we got carried away there a bit in a good way. So we left Cogent for a bit, started working on termination checkers for lambda calculus. That was fun. Yeah, we want to verify more data types and drivers using Cogent and Dargent. Yeah, we're also adding a limited form of arrays, and that is not too difficult. Fixed size arrays, no linearity and arrays together, just arrays of unboxed things. If we want to do linearity and arrays together, things get way more difficult, and we need to add support for refinement types. We have several tiny prototypes of that are very far from finished. Yeah, I want to improve the verification interface, so horizontal composition between Cogent and C. We've looked a bit at language-based security, information flow. Linear types are nice, so you can track things. There's the MAX system, I don't know, access control, Marco Vecina and Alejandro Russo and others. They use monads in Haskell to track information flow control, some relationship between monads and linear types. We started looking at how to extend the language to support information flow security, just at the source level. No secure compilation quite yet, unless someone wants to support this project for the next 5 years or something. Also looking at concurrency. Again, leaving Cogent a bit and looking at simpler languages, and then maybe going back at some point. Yeah, that's all. If you want to do something with Cogent or Dargent, they're public, they're on GitHub. Please do. We've had a lot of support for the Dargent project, industry support for the Dargent project. I've changed institutions, and these projects are now finished. So if you want to support this project, please do. If you have people who just like new languages and want to try them out, please do. We're happy to get feedback about the language and continue to improve it. Yeah, thanks everyone for listening. And
all right, I see people are lining up for questions. That's great. Remember to state your name for the benefit of everyone, but especially the online audience. Ed?
Hey, Adam Trapala from MIT. I have 2 questions about the recursion feature that you're adding. It sounded like simultaneously you're working harder than I would expect to put that feature in there, but also missing an element that seems important. For the first part, you said you're adding primitive recursion only, but still you have to prove termination. That's surprising. And for the second aspect of that, you didn't mention proving stack space usage bounds, which seems really important for systems code that kind of generalizes termination. So how do I make sense of both of those together?
Okay, I said primitive recursion, I lied. We started with primitive recursion and we're greedy. So we wanted to extend that to bigger classes of functions that terminate. And that's what got us off track with the more interesting, on track, off track, I don't know, on some track with more interesting termination checkers. What else?
Stack bounds?
Stack bounds. You're saying that's important and we should look at how to bound the stack
in a kernel, you don't generally assume your stack will resize dynamically if you're in out of space.
Yeah.
Okay, future work.
Yeah. I don't know if any of these recursive type features will be used by systems folks. I think I need to talk to more people in the PL community who have been in the PL community for longer to understand how recursive data types are flattened into arrays and optimized and whatnot, and when that's possible and when not, because that was kind of my intuition of what needs to happen, but I don't know when I can flatten a recursive structure into some array, and what is reasonable amounts of memory to use at once, and what to do once that runs out. I'm sure there's a lot of things that compilers do out there. happy to learn from it. I'm happy for people to refer me to material to learn from it, because I really don't know how that's handled. But yeah, that's yeah. These were the two questions, or?
Those are the questions. Thanks.
Okay.
This side.
Hi, Gabriel Radan in RIA, France. Thank you for the talk. I enjoyed it a lot. One big part of the project was to basically raise a little bit the level that you have in embedded code and make them use algebraic data types.
Sorry, I don't hear you.
One big part of the project was to raise a bit the level of code that they have in embedded code and try to make them use algebraic data types in a way. How have embedded programmers reacted to that? Did you try to educate them a little bit? How does that work?
So we haven't really used this on embedded systems.
Or drivers and all these kind of things, low-level code in general.
I mean, yeah, unfortunately, we verified just 2 drivers, and mostly PL and verification folks did that because we do not have too many systems folks around at the moment. So, the first time when we had systems folks around and we presented this language, the requests were endianness, and the other one that I'm still working on is going to take a while, which is dynamic size arrays with objects inside, like tags. But it was not that people wanted to implement bits and bytes in memory. They were happy to abstract away from that. It's just that they wanted very specific code and very specific data structures to come out at the other end, and if we could provide that, they'd be happy to use it. That was my impression. It's a very skewed population of systems folks, because they're SEL4 folks, and they are happy bending over backwards to get their verification working. So, but yeah, no, I think in this particular instance, actually, it was exciting for systems folks, because one thing is they do need to do the marshalling, unmarshalling, serialization, deserialization anyway if they use any sort of algebraic types on the C side. And just having that go away meant that they get more efficient systems, and people are happy with that.
Okay.
Let me try to relay a question from online from Rizkallah. Are layout specifications sufficient for ensuring atomic reads and writes? So I see concurrency is on your future direction, but I'll try to generalize this a little bit. That when you're dealing with device drivers, there's often some inherent concurrency, and you have to worry about half writes or something like that. Does that show up at all?
It didn't show up for us. What did show up is another thing that we're looking at is when you have sometimes you have these what are they called, volatile registers, so you don't know what value you'd get out of them, and there is a way to handle it through the current Cogent infrastructure by just abstracting over that, saying I get some value from this, and abstracting over what the value is, or just basically how random numbers are generated. So you have the random generator getting a seed, and then it's deterministic, but then you abstract over the seed and you just see the random number. So I've done something similar here and just pass this additional seed parameter and then abstract it away at the other end, saying you can just have one layer of abstraction on top of the higher order logic code that you get, where you abstract away the seed, but you have to know what the seed is to abstract it away. We don't do that automatically. I just did it manually to try if it works. And if you abstract it away, then you can pretend that the value is non-deterministic. And that works. I think there are other ways to improve this so it works in an easier manner, which is basically allowing the specification of foreign functions, for example, to be non-deterministic. But yeah, it works. It's a bit annoying, but it works.
Thank you. Let's go back up here.
Hello, I'm Facundo Dominguez from Twig, and I wanted to ask, do you have any expectations or impressions on how much the Cogent and Dargent approach could reduce the verification of CompCert or CEL4 if they were to be done again?
To do what, sorry?
To certify Cell 4 and CompCert.
I'm not sure what you mean exactly, but like I can imagine having something like Dargent for C and having something like the CompCert compiler ensuring some certificates about layouts. For SEL4, I think operating systems typically do a lot of sharing, and Cogent is good for components that don't involve much sharing. When you have a system that involves a lot of sharing, you won't get as much mileage out of such a language, I think. I'm not sure if that's what you mean, like re-implementing an operating system in Cogent.
Because these two projects were proposed as the examples of very expensive verification, I think, well, maybe now that we have approaches like Cogent and Dargent, when we could get those down, but I wonder how much.
Okay, I see what you're saying. So I think it was more proposed as a motivation for why it's important to have efficient systems and also not compromise on trustworthiness. But like for the Cogent language in particular, like we've looked at file systems and device drivers and the sort of systems that don't have a lot of sharing, and that's why linear types were the right answer for this domain. Maybe some other language would be good for abstracting on operating systems further. Cogent relies on a tool called autochorus that abstracts a deep embedding of C, so C semantics into monads, like a shallow monadic C or a monadic representation in Isabelle Hall. SEL4 verification was redone, I think, using autochorus, I believe, or at least some large portions of it, and it was shown to be good for that. So I think like more abstraction's good. You just need the right type of abstraction, and I don't think Cogent's the right type of abstraction for implementing an operating system. Dargent could be a good idea for other languages and other compilers. Nothing about it has to do with linear types or is specific to Cogent in any way.
Thank you.
Hi, Mike Strober, Active Group. So it seems a number of projects in the formal verification space rely on formal semantics of C, right? And I think you just implied that you're sharing the same semantics between the SEL4 and your project.
Yeah.
CompCert presumably has a different one, having been written. Is there any reuse between these specifications, or how do you know they're correct?
Sorry, you mean can we use CompCert semantics instead of SEL4 semantics?
No, but is there, do you know that it's your semantic model is consistent with Cox? I mean, or generally?
It's not.
Okay.
None of them are consistent with one another.
Okay.
I think the semantics of C is underspecified, and each of them specifies the bits that are underspecified differently.
Okay.
I don't know if we're using any parts of that or not. I haven't thoroughly looked into it. Talking about COC, though, one other project I haven't mentioned that started and is supposed to keep going is we're trying to have a verified compiler from Cogent down to LLVM using interaction trees. I know there's the Helix compiler that was verified that way, and that was exciting. I want to do it too, but I'm not planning to port the whole infrastructure to COC, just the lowest level of verification, just to.
Thanks.
But yeah, like until I've done it, I don't know. I don't think there are any. Sorry.
Great, we got two last questions.
Hi, Elias Sergey from NUS. Hi, Christine. Fantastic talk. Thank you. Thank you so much for that. Okay, I have the following question. So imagine I'm a systems programmer turned PL person, and I'm a client of your tools. I'm using Cogent and Dargent, and I write the DSL program, and they produce a bunch of verified C code. Awesome. And then I look at this C code, and I don't like it. It's not as efficient. It's not as idiomatic. For whatever reason, I want to rewrite some parts of it. What about the proof? So what's the story there?
There's no story. I mean, Jenko gave us a half story of write your own C, like create Cogent out of that, compile it back to C. Never look at it. It will be efficient, we pinky promise, but don't look at it. And or another thing that we've tried, but again, it was a student project, it still needs a lot of development for it to become a thing, was having debugger. So that's what most systems folks complained about. So they didn't like our C code that we're generating, but they're like, okay, I can live with that as long as you can give me a debugger that that matches the C and where it came from in the Cogent, so that I can look at the Cogent, look at the C, and know exactly like link them. So we've started implementing, or like we have a rough implementation of a debugger for Cogent that does that. But yeah, if you want to implement your own C code, I don't know. If we can link it with other Cogent, we could convert it to Cogent and convert it back. I don't know what else to do with it beyond that.
Thank you.
Last question.
Nick Swami, Microsoft Research. Great talk, Christine. I really enjoyed it. It's great to see this working in this small TCB setting that you're using. I just wanted to point out that if you're willing to adopt a somewhat larger TCB, including an SMT solver and a tool chain like FStar, there's a great library called Everparse that my colleague Tahina there has been building, which supports some of the kind of data layouts that you're talking about, including general arrays and refinement types and dynamically sized arrays and things like that too. So.
Okay, I'm happy to talk about it. Yeah, so I think it's nice to have as much like verification as we can, right? But like, again, it's a compromise sometimes of like just on top of the compiler theorem that we get, the higher order logic, if we can go a few steps further automatically using SMT solvers versus not do that at all because we don't have the manual labor to do the manual proofs, by all means, something's better than nothing always, but like, sometimes actually, but like, yeah, I'm happy to talk about it. I'm not sure how adaptable it is to Cogent, but like, I'm definitely happy to talk about it because refinement types were much harder to deal with than I anticipated. Because we wanted refinement types with interactive proofs as well. So bubble up as many automatic proofs as possible, and then bubble up the rest to a person to prove, and that was not as easy as I would have liked it to be.
Thanks.
So.
Great. Let's thank Christine one more time.